has taken a stand of, I'm going to build these mega pump stations and keep the drainage canals that exist down to a certain level so that there's no pressure on the dikes. It's your job, local municipalities, to get the water into those canals, and I'll keep them at the reasonable level. So it's really a major change in philosophy.
They have two canals. It's the Harvey Canal that is coming down this way and the Algiers Canal. They meet at a point. The pump station's a few hundred yards beyond that. 60% of the flow comes down the Algiers Canal, 40% of the flow comes down the Harvey Canal. So what the Corps of Engineers is trying to do is prevent a storm surge from backing up into those canals. So they put a closure gate there. So once the gate is closed, you prevent the storm surge, but they still have the water collection. And you have to pump water past that gate, which is what our pump stations do.
The goal for this pump station is to have it ready with flood protection for this region by hurricane season 2011. So we're at the pump intake, which is 18 feet below water level. This pump intake was submerged in concrete about 5 months ago. The pump discharges 30 feet above on the other side of the station. All the engine and pump accessories get mounted about 50 feet above where we're at now. We have about 800,000 gallons a minute coming through this channel that goes into the pump in this direction.
This contract has a Department of Defense priority rating. When we go to a vendor, we make them aware of that. And we have had to bump other work that they were doing off of the machines and demand to have our pieces put in and machined first.
Each component was subcontracted to various vendors across the country. There's 10 major components, but literally hundreds of parts that had to be coordinated to arrive at assembly at the same time.
We have to keep track of where everything is at all times so that we know we can have our shipper ready to pick up a piece and take it over from fabrication to paint, and then paint down to our assembly vendors down in Louisiana.
Each pump is in a various stage of manufacture. It's not a serial process. Once all the components are at the assembly site for assembly, then the challenge becomes actually putting the components together in the proper order so that the pump is actually built to the engineering specification.
Here we got the propeller housing. It's the first piece that goes on. Over here we got the truncated cone. This is the last piece that goes on. It's the very bottom of the assembly. What we have to do is pick up the entire assembly, weighs approximately 120,000 pounds, and stick it on this piece. Over here we have what we call the column. It's the very top of the assembly. It weighs approximately 9,000 pounds. Behind me we got the pump propeller. It's a 19,000 pound stainless steel propeller. What we're doing right now is cutting the keyway in it. We got a keyed and balanced propeller, and what we're getting ready to do is drop the shaft into the propeller, and then after that we move it into our propeller housing and assembly stand. Then from there we take this diffuser unit, slide that over the shaft, and bolt it down. Right now we're dropping the shaft and propeller. We stick it through the bottom of the propeller, and from underneath we install a propeller keeper plate which secures it to the shaft and propeller. That means we got it in.
This pump is a 140-inch propeller pump. The prop diameter is 10 foot. The bowl assembly weighs 52 tons. There are 11 pumps on this project. Each pump is rated for 1,740 CFS. That's approximately 800,000 gallons of water a minute per pump. So you can imagine, by the size of this unit, it was a huge undertaking to coordinate the delivery. The contractor asked us to accelerate the schedule of the job. This acceleration was required so the pumps could be installed in the bays prior to the roof being put on the building. This helped the contractor and saved him time in the long run.
We're now standing at the discharge channel at the pump bay. This is the side that all the water comes out. We have our model 140-inch 8211 vertical propeller pump. They're going to lift it with a 600-ton crane and put it back over here in the pump bay. It's been trucked here in the horizontal position, partially assembled. We've turned it vertical and completed the assembly process. It's rated at 800,000 gallons per minute.
Because of the importance of this project, every component went through a QA process. The first pump had 630 pages of quality documentation that was required to show that our pump met the requirements of the specification.
It's mainly just really nailing the hydraulics. The pumps are way too large to physically test them other than in the field when they're installed. And so what you do is you base it on a model of affinity laws. Approximately 3 months after award, we were running model tests. We had 18 people show up for a week-long model test. When we were done, we took our model of propeller and we put it across a coordinate measuring machine. The largest discrepancy we had on an 18-inch diameter propeller was about 12 thousandths, which is about as accurate as we could really measure it. That was the most important thing, is just get the model to actually be truly accurate and reflect what we had done on our development to make sure that the hydraulics are peaked. And we did a good job of hitting that.